Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 4 of a little mini series within that playlist that I'm calling Balanced Incomplete Block Design. And in part 4 we're going to look at the sum of squares error and the partial F test that's used in the Balanced Incomplete Block designs. Now, as a reminder, our model is y equals x beta plus epsilon. And we partitioned it into two. So x beta, beta, and that's for the blocks, x tau, tau, that's for the treatment assignments and the error. And then I'm going to push you off to part 2 in more details, where we added a well-chosen zero to this design and we came up with this. So there's two pieces now, alpha and tau. And tau are the same as these tau. And the design matrix is x beta and I minus m beta, which is the perpendicular projection matrix onto x beta, and then times x tau. Epsilon is still multivariate normal, mean vector 0, variance covariance matrix sigma squared I. Now, in the 9th video in this playlist that I called Estimating the Air Variance, we looked at the sum of squares error in a lot of detail. And it's essentially this. The sum of squared error is this quadratic form, y transpose I minus m y, where m is the perpendicular projection matrix onto the column space of m. But in part 2, we noted that m is m beta plus m tau, where m beta is the perpendicular projection matrix onto the column space of x beta, and m tau is this expression, which is the perpendicular projection matrix onto this column space. So thus, the sum of squared error, we can replace m with m beta plus m tau, which is what this is. And then we distribute the y's into each of those. And then we just fill in basically what m tau is. So this carries down exactly, and then m tau is this long expression right here. Okay, now the reason I write it in that long expression, you'd think, well, just keep it like this. Well, I want to show you what they do in books that mainly deal with scalar notation, and they write it like this, and then the way they manipulate it, they create these sums of squares. And if we think of this as I minus m beta, notice there's one here, one here, one here, one here. And then it's what we pre and post multiply. So they call this SSYY, and they would call this SSYX tau, right? YX tau. This would be SSX tau generalized inverse, sum of squares x tau y. And anyway, so in a lot of books, they create these tables that you add up certain things, and you hold them in this table, and then you sum them all, and boom, you get the sum of squared error. But really, you could just use this piece right here, and we're done. And it's actually so cool. I can't wait to show you the R program that deals with all of this. I have a video called Distribution of Quadratic Forms. I think it's in either in the matrix playlist or the quadratic forms playlist. And the sum of squared error divided by sigma squared is a central chi-squared with rank I minus m. And since this is a perpendicular projection, it's actually the trace, in which the degrees of freedom is bk minus b minus a plus 1. And also we derived this in this video here, estimating the air variance. So let's look at calculating this degrees of freedom. So the rank of x is a plus b minus 1. And if you look at the way x is created, there's a column of ones, and then a columns associated with the treatment and b columns associated with the blocks. And it's easy to tell that it's a plus b minus 1, the rank. Now, the way we have reconstructed x, notice that x beta is orthogonal to I minus m beta x tau. So what's going on there is we take x and we reconstruct it into this x beta and I minus m beta x tau. It actually looks so different, but mathematically they're 100% equivalent. So we construct it into these two orthogonal spaces. So then the column space of x is equal to the column space of this. And since those are orthogonal, the rank of x is actually just the addition of the rank of each of these. But the rank of x is a plus b minus 1. And it's so easy to tell that the rank of x beta is b. And you subtract that over, then you can easily see that the rank of this piece is I minus m beta x tau is a minus 1. Okay, so this is a little background before we start calculating the degrees of freedom here. So that's it. Now here's another general result, that if we take some matrix, pre-multiplied by the generalized inverse of A, and then we post multiply by the same thing, notice that this right here is A, so we get it back. And the important note there is that this is idempotent. And so if it's idempotent, then the trace and the rank are the same thing. Okay, so the rank of m tau, since it's a perpendicular projection matrix, it's idempotent, so it's equal to the trace. Now remember, m tau is this piece here. So we say the rank of m is equal to the trace, but the trace, we can move this piece to the back. And that's what I do here. Now notice we have a matrix pre-multiplied by its generalized inverse matrix. So it is idempotent. So this trace is actually equal to the rank of one of those. Now this is an idempotent matrix, so the rank of this is actually equal to just to the rank of half of it. But we just said the rank of this piece is a minus 1, right? So the rank of m tau is a minus 1. Now the rank of m beta is the rank of this, which is, it's a perpendicular projection matrix. But this x beta has an extra column of 1s, which makes this not full column rank, why we have to take the generalized inverse. But the column space of x beta is equal to the column space of x beta star. And this, it's 100% the same, except for it doesn't have that column of 1s. But then when we take x transpose x, it's a full column rank, so we can take the inverse. But this is still the perpendicular projection matrix, so it's equal to the trace. But we take the trace, then we can move that to the back. And then this is the identity matrix of a B by B matrix, the identity matrix, so the trace is B. So the rank of MB is B. So now the rank of I minus M, since it's it's idempotent, it's the trace, and it's the trace of the individual ones. But this is so it's equal to the rank of each of those. And this is a BK by BK identity matrix, so it's just BK. The rank of this is B, the rank of that is A. It's A minus 1, but the minus makes it A minus plus 1. Okay, so that's how we get that degrees of freedom there. So now the test of no treatment effect. So, is the overall mean, treatment vector just equal to the overall mean? That's what this says. Or is one of those components different? And that's for some I equal 1 to A. Now, we want to test, is there a treatment effect? So we look at the reduced model, right? We get rid of the taus, and we look at this, and we look at the sum of squared error. So that's why there's a S0 here. On the previous page, we had a S1. So this is a sum of squared under the null hypothesis, and the full model is the sum squared under the alternative hypothesis. Now here, since we got rid of the taus, M is the M beta is the perpendicular projection matrix on the column space of x beta, and that's what we want. So this is the sum of squared error, and it is distributed with a central chi-squared with b times k minus 1 degrees of freedom. Now the test statistic, or the partial F test, is the reduction in the sum of squared error when we add those taus to the model. So that's what we're looking at here. And so this is a chi-squared, and then we divide it by its degrees of freedom, which is the difference in the ranks. And this is the sum of squared error for the full model, and divided by its rank. And each of these are independent, and so we get an F test. But now if we start plugging in what we know, sum of squared error under the null hypothesis is this, sum of squared error under the alternative is this. Now we can distribute the y's, and this cancels with that, and we're left with this right here, y m tau y, and that's divided by its degrees of freedom, divided by s, the sum squared error under the alternative, divided by its degrees of freedom. And so under the null hypothesis, that's a central chi-squared with a minus 1, and then denominator degrees of freedom, this. Now what is so cool, and I actually can't wait to show you the R program on this. Another way to think about this is we could partition this total sum of squares into sum of squares block, sum of squares treatment, sum of squares error, like this. So yi minus j y is sum of squares total. Now if we add zeros, which is we add m and subtract m, but in this m we replace it with m beta plus m tau, which is what this is. I just moved it differently, kept this the same. Now we distribute y to here, which is what this is, y to m tau, and y to m beta plus j. And so this is the sum of squared for block. This is the sum of squares for treatment. They often call it the sum of squares for treatment adjusted, and this is the sum of squared error. But notice that the sum of squares treatment is the same as this partial F test. So we're actually testing, is there an effect of adding the treatments? Okay, well that's all I have for this video. In the next video we're going to introduce some notation if you really want to delve into the theory of incomplete block design. We're also going to derive some properties that we will need when we look at contrast in this setting. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.